Log on, tune in, find out. Another good idea from Cambridge.
Well, thank you very much, and thank you to the organizers. Well, you already heard about compression yesterday in Mark Sapir's talk, but I understand that there will be some overlap, but not too much. So let me start by, well, definitions. So XD will be a metric space, and F from X to LP, Lipschitz map. And then you define the compression of F as the supremum of the set of alpha in the interval 0, 1, for which you can find positive constants such that the distance in the target space, namely in LP, is bounded below essentially by the distance in X to the power alpha. And so to be more precise, we allow some constants, one multiplicative, one additive. So C of dxy to the alpha minus capital D is less than the distance in the target. So we compare the distance in the target space LP to the best possible power of the distance in X. And then we, taking the supremum over all possible F, we get a numerical invariant for X, which is called the compression. Oh, sorry, the LP compression. Alpha sub P of X is then, so the compression of X. So that's the supremum of the compression of F taken over all Lipschitz map from X into LP. And okay, my background being in representation theory, I'm interested in groups and group actions. And so, well, when you think about metric spaces, of course, they come with their isometric groups. And so, if G is a group acting isometrically on X, you define the equivariant LP compression alpha P sharp of X by restricting to equivariant embeddings into LP. And here, of course, I have to say, how does the group G act on LP? Well, it will act through some affine isometric action, where G acts on LP through some affine isometric action. Okay, so in particular, when the group G is a finitely generated group, you may turn it into a metric space using word length. And you get alpha sharp P of G, so the equivalent compression of G. And with the obvious inequality that it will be smaller than the compression, the non-equivalent compression, because there are less equivalent maps than usual maps. And okay, let me draw two diagrams that connect this compression and equivalent compression to other notions that have been discussed recently in the literature. First, if you have a space X and you assume, hold on, oh yeah, this is alpha 2. So that's, if you assume that this space has a positive Hilbert space compression, then, well, clearly this implies that X is coarsely embeddable into Hilbert space. And this property of being coarsely embeddable into Hilbert space is implied by another property, which is that X has a Gaulian-Hughes property A. So property A is a property of metric spaces that will or will not be mentioned in this workshop. And it's a very weak form of amenability. And Gaulian himself proved that X, well, this property implies coarse embeddability. And it is known that now if the Hilbert space compression is large enough, namely larger than 1/2, then this implies that X has used property A. And this is a result by Gantner and Kaminker. So this is one interest of compression in the sense that it's related to other properties that have been widely studied in geometric group theory, but also in operator algebras. So this is the situation for spaces, and in the case of groups, actually we know a little bit more, in the sense that, well, if the equivalent compression, the LP equivalent, oh, here let me assume that P is not 1. If the LP equivalent compression is positive, then this implies that G admits a proper isometric action on LP. And for P equal 2, this has a name. This is equivalent to the so-called high group property. And Gromov has another name for that. Gromov calls this property AT amenability. And again, this admitting a proper isometric action on LP is implied by amenability. Amenable is implied by amenability of G. This is a result that I proved long time ago with Becker and Sherix back in 1993. And amenability itself is implied by the fact that LP compression is large enough. And large enough means that it's larger than the max of 1 over P and 1 over 2. And this is a fairly recent result by Naor and Perez. So again, we have the similar kind of diagram for spaces and groups, and this highlights the fact that in some sense use property, well, for me this really shows that use property A is a weak form of amenability, and similarly for coarse embeddings. And also, to end this introduction, I should mention that if G is amenable, then the equivalent compression coincides with the non-equivalent compression. And this result has a long history. For P equals 2 and G abelian, this goes back to a paper by Aharoni, Moret, and Mityagin. For P equals 2 but G arbitrary, this is a result by Gromov in 2005. And for P, for any P, for P arbitrary, this is a recent result by Naor and Perez. And okay, so when you have a new invariant for spaces or for groups, well, of course you may ask two kinds of questions, and the first question you may ask is, of course, can you compute it? And here is a quote from one of the two papers by Naor and Perez. The difficulty in evaluating compression exponents is the main reason for our interest in this topic. So Terry Tao has a paper on what is good mathematics, and I'm not sure he mentions difficulty, but of course he mentions as number one problem solving. So okay, to be faithful to, and the other question you may ask is, how does this invariant behave under various space constructions or group constructions? And okay, let me give one example which I believe is new. And let me talk a little bit about the so-called bomb-slack solitaire groups, which this is a classic in geometric group theory. So they depend on two integer parameters, m and n, and actually they are given by a presentation. Namely, these are groups with two generators, A and B, submitted to one relation, which is that B inverse AM B is AN. Namely, B conjugates AM into AN. Did I say? Oh, okay. I think I got it wrong. Well, AN, AM this way. And, well, okay, here's the theorem, which is due to Yves Cornulier. That if you assume that M and N are at least two. Oh yeah, if one of the exponents is 1, then the group is solvable. And so this is really special. And they start being more interesting, let me say, when both of the exponents are at least 2. And Eve also has to assume that they are not equal. You'll see why in the proof, which I'm going to sketch. And what he proves is that for p in the interval 1, 2, the equivariant LP compression is exactly 1 over p. And let me give the idea or sketch of proof. First, we know that because the exponents are larger than 2, this group is non-amenable. And this gives, and using the result by Naur and Perez, this gives immediately that the equivalent compression is at most 1 over p. So by non-amenability, so this is at most 1 over p. So we must prove the other bound. And we may view G or BSMN as what is called in group theory an H&N extension. So start with the cyclic subgroup generated by A. And that's Z, that's a copy of Z. And inside we have two subgroups. The one generated by A to the M, and the one generated by A to the N. So we take M Zn and N Zn, and what B does is implementing an isomorphism between these two subgroups. And actually it's the universal group doing that, and this is the so-called H&N extension. And the point is that there is the Basser theory on groups acting on trees, which applies to H&N extension, and which gives us immediately an action on this group on the M plus N regular tree. So this gives an embedding of BSMN into the automorphism of T M plus N, and this is the M plus N regular tree. Okay, this is already something quite interesting, but the point is that when you work out the image of BSMN by this homomorphism, it turns out that this is a non-discrete subgroup of this automorphism group. And so to make it discrete, you need a trick, which is to map BSMN non-injectively to GL2R, so 2 by 2 matrices with a non-zero determinant. And you map the generator A to that unipotent matrix, and you map the generator B to this diagonal matrix. And it turns out that when you work out the relation, you see that it satisfies. So this gives a homomorphism which is not injective because the image here is a solvable group, and the group we start with is not solvable. And we see here why we need n distinct from m. That's the image. If n is equal m, the image is really too small. Anyway, using the diagonal embedding, we may let BSMN act on the product of the m plus n regular tree and the upper half plane. So where on GL2R will act by fractional linear transformation. And so, and of course, this guy, the H is endowed with the usual non-Euclidean metric. And okay, the crucial part of the proof, which I'm not going to explain, is the fact that the orbit map from BSMN to Tm plus n cross H that takes a group element G and maps it to Gx0. X0 is some base vertex and G applied to I, so complex number I. This orbit map, of course, will be G equivariant, but the non-trivial fact is that this is a bi-Lipschitz embedding. And this basically ends the story, because so you embed discretely now this group into this product space, and what was previously known is that if you take any tree and look at its equivariant compression, LP compression with respect to the full group of automorphism, this is at least 1 over p. And if you do the same for the hyperbolic plane with respect to its group of isometries, oh, okay, and it's also 1 over the LP compression. You also get 1 over p, and using this gives you the reverse inequality, that the compression is at least 1 over p. Okay.
It's a minimum. It's not maximum. It's a minimum, right? Because you're using minimum, in fact. Maximum.
It's using maximum. Yeah. P is between
then
1
it's
and
not
2.
understand why.
Relation between
Max,
1
P
and
is
2.
less than 2 here.
Sorry?
P is less than 2. He's using P less, this is for P less than 2.
Yeah, P is between 1 and 2.
Yeah, in
It's less than 2. Sorry.
no, in this result, p is between 1 and 2 for that result. Okay. Where
So for p greater than 2, this is not known, right?
it's not known. It's not known. Well, okay, it's at least 1 over p. But yeah.
It's a half.
Pardon me?
It's a half because of P equals 2.
Why is that?
If p is greater than
Covariant compression is always at least that for L2. Alpha p is always at least alpha 2. And alpha 2 you just proved it equals 1/2.
Yeah, and then but for p greater than 2. I think this is Mark's question.
It is greater than 2.
Yeah, so the upper bound is a half because of that.
Yeah, the upper bound,
and the lower bound because you proved it for p equals 2. So it equals 1/2.
I think, okay,
The case p equals 2
yeah.
implies that it's at least a half for alpha 4, for example.
Oh, okay,
And the upper bound is follows from that.
okay. Then, okay, if I'm ready to believe you. So this means that for p greater than 2, it will be alpha sharp p will be 1/2.
There's a theorem here, which is alpha p is always at least alpha 2. Alpha p sharp is most at least alpha 2 sharp.
Was also, yeah, I see.
Once you know that, then you're done.
Because I understand.
Okay. So now, as I said, the other line of research is what is the behavior of an invariant under various group constructions, and okay, well, so here we'll focus on compression for groups under group constructions. And to start with a trivial example, the compression of a direct sum is the minimum. Of the compression, and same for LP for equivalent compression. So same for alpha p sharp. Now to pass to less trivial stuff. Here's a nice result by Shun Lee. And I should say that this followed the previous results by Naur and Perez. And it's about compression of Riesz product. So the Riesz product of, so you take, let's say, two finitely generated groups, G and H, and the Riesz product of G with H is defined as follows. First, you take copies of G indexed by H, and take the direct sum. And here H acts by shifting indices, so you are allowed to take the semi-direct product. And you get, this way you get the Riesz product. And what Lee proved is that there is a interesting lower bound for the Riesz product, for the LP compression, which is that this is larger than the maximum between, well, 1/p and 1/2 times the minimum between the L1 compression of G and the L1 compression of H divided by 1 plus alpha 1H. And similarly, for equivalent compression. So that's a nice result. And I want to discuss now other constructions that you may perform.
Is there any upper bound?
Well, the minimum of alpha pg and alpha ph, that's just because g and h embed into isometrically into this risk product. But okay. No, I don't think there is any better upper bound. But so let me mention amalgamated products. So we consider the amalgamated product of two finitely generated groups over F, which is a finite subgroup. And okay, oh yeah, to avoid trivialities, we also assume that the index of F in G1 is at least 3, and the index of F in G2 is at least 2. So if they are both 2, we get the infinite dihedral group, for which we know everything. And okay, so in this case, this guarantees that the group is non-amenable. And here's a theorem which was obtained by my student Dennis Dresen last year. That first, and okay, oh yeah, this is only for the Hilbert compression, and I will give you one sketch of a proof, and you'll see why we are, well, so far we're stuck to Hilbert spaces. So that the equivalent compression of G of the amalgamated product is the minimum of the equivalent compression of G1, of G2, and of 1/2. And that's an equality. Question?
What is this product?
What is the amalgamated product? You know what a free product is? Okay, it's a free product. So you take all. Okay, let's say that you have two groups. Maybe I should have called them A and B. So to get the free product, you write all words which are in alternating, like A1, B1, A2, B2, AK, BK, where the AIs are in A, the BJs are in B, and the group rule is just concatenate. And if you have two B's, you multiply them into the group. And that's how you multiply. So that would be the free product. But here you are given a finite subgroup F, both in A and in B.
That's fine. Yeah.
I think I wrote it. and you glue together. So you quotient this free product by imposing relations that the copy of the copy of F inside A is the same as the copy of F inside B. So that's the so-called amalgamated product. Where did there it is. And for the non-equivalent compression, we have that the minimum of alpha 2 of G1, alpha 2 of G2, and 1/2, we just have two inequalities. So this is less than alpha 2 of G, and this is less than the minimum of alpha 2 of G1, alpha 2 of G2. And maybe let me give you an idea of of the proof of let's say of the first part. So and the reason why we are stuck to Hilbert spaces is that we work with so-called conditionally negative definite functions. So, and we use the fact that there is this bijective correspondence between, on the one hand, embeddings of G into Hilbert space, and on the other end, conditionally negative definite functions on G. And so, for instance, to get the lower bound so that the equivalent compression is larger than this minimum, which is the non-trivial part. So, of course, we may assume that both compressions are non-zero. So, assume that alpha 2 sharp of Gi is positive, so for I being 1 or 2. And we take an epsilon, which is in between 0 and the minimum on the right hand side. So alpha sharp 2 of G1, alpha sharp 2 of G2, and 1/2. And we know that both G1 and G2 admit embedding, which are let's say better than word lengths to the epsilon. And this allows us to find conditionally negative definite functions psi, psi 1, or let's say psi sub I on G sub I, so psi 1 on G1, psi 2 on G2. We use the fact, well, actually, Dennis uses finiteness of f by allowing, finiteness allows you to assume that this function vanishes on the finite subgroup f. And because it comes from an embedding which is better than epsilon, oh yeah, maybe I should have recalled how this bijection is working. So whenever you have an embedding f into Hilbert space, you take the squared, the norm squared of this embedding, and this gives you the conditional negative definite function. So so we know that psi I of G is larger than G to the 2 epsilon, and maybe with a constant C. And the point is that there is a normal form for elements in an amalgamated product. So we use normal form, And it's slightly more complicated than what I explained to answer your question, Mano, namely that the normal form goes as follows. It's A1, B1, A2, B2, AK, BK, then F, where F is an element of the finite subgroup that we amalgamate, and the AIs are representative for left cosets of the subgroup F in G1, and the BJs are representative for left cosets of F in G2. And then we define a new function psi of G just as the sum of psi1 over all the AIs plus the sum of psi2 over all the BJs. Okay. Because by uniqueness of the normal form, this is well defined, and it turns out that this is conditionally negative definite. And okay, and from this, using using the lower bound that we have on each on psi1 and psi2, it's not difficult to see that psi of G will be greater than C to the G to the 2 epsilon minus some constant. And this constant appears because in this formula the element F does not appear anymore. So at some point, because of the triangle inequality, we have to subtract the diameter of this finite subgroup F, and this gives this negative constant. But that's basically the result.
In order to have this normal form, don't you need F to be a normal subgroup?
No.
No, because the left cosets.
No, it works for any subgroup. Yeah, you have to specify in which direction you take the cosets. In either.
I see.
And okay, it was 3A. So then it also has a result for HNN extensions. So here, well, with a similar type of assumption, that namely that F is a finite subgroup of H. So H is finitely generated. F is a finite subgroup. Theta is some monomorphism. So some ejective homomorphism from F into H. And yeah, unfortunately, he has a more serious assumption to put here, namely that if the subgroup generated by F and the image of theta, that this subgroup is finite. And then the theorem, again due to Dennis Dresen last year, was that first, for the equivariant L2 compression of G, we have an exact formula, namely it's the minimum of 1/2 and the equivalent L2 compression of H. And for the non-equivalent compression, we just have that the minimum of alpha 2G, so what am I saying? Alpha 2H and 1/2 is less than alpha 2G. This is less than alpha 2H. Note that the second case, reduces almost immediately to the case of free product. Indeed, there is a result by Papasoglu which tells you that G is quasi-isometric to the free product of H with Z. And since compression is a quasi-isometric invariant, you reduce immediately to the case which I discussed before, namely compression for free or amalgamated products. And okay, the last thing I wanted to discuss is the case of extensions. So here, what I mean by that is that, okay, assume we have a normal subgroup and a quotient, and we can say something about compression of N and Q. What can we say about compression of G? And let me start with a caveat that, well, we're going to reduce to, well, actually, we are not talking about equivalent compression for this part. Not talking about alpha 2 sharp for the reason that it is known that the so-called Hagerup property, so the fact that the group admits a proper isometric action on Hilbert space, Hagerup property is not stable under semidirect products. And the standard example is the semidirect product of Z square with SL2Z. So you let SL2Z act on Z square just by matrix multiplication, and there is a result which is equivalent to something that Kashdan proved back in 67. That every isometric action of this semidirect product on a Hilbert space as a fixed point under the normal subgroup Z square. So it has a Z2 fixed point. So this means that there is no equivalent proper embedding of this group into Hilbert space. And actually, this can be phrased as follows, that alpha 2 sharp of Z square we know the value. It's 1. Alpha 2 sharp of SL2Z. We also know the value, and it's 1/2. While alpha 2 sharp of the semi-direct product is 0. So this means that, well, we cannot hope for a lower bound for alpha 2 sharp for equivalent compression. So all we can hope for is a lower bound for non-equivalent compression. And here's the final result by Dennis that I want to mention. Okay, so let G be finitely generated. So assume we have a short exact sequence like that, and we endow n with the length function induced by G. So this means we are not assuming that n is finitely generated. But we view n as a metric space with the induced distance from the word length of G. And then first result is that if Q has polynomial growth, then of course alpha G is less than alpha n, but alpha G is larger than alpha n over 3. And the second distance is that the second result is that if Q is hyperbolic in the sense of Gromov, we get that alpha n over 5 is less than alpha G, which is less than alpha n. And and it's about Hilbert compression, so I should put 2 all over. And maybe let me conclude by recalling an example by Naor and Perez, which shows that the obvious bound that alpha 2G is less than alpha 2N, this lower bound, well, it may happen that here we don't have an equality. And but they treated the case of the Riesz product of Z with itself. And of course, there is an obvious map to the integers. So call N the kernel. And what they proved was that the Hilbert space compression, okay, with some help by Tim Austin, I guess. Oh, well, okay. Let me write. So the Hilbert space compression here is 2/3, while the Hilbert space compression of the normal subgroup is 3/4. So where did Tim help? Here probably.
The upper bound that is at most 2/3.
Okay. So okay. Anyway, with some help from their friends, and yeah. So this means that. So this is a case of where, of course, the quotient is Z, so it has polynomial growth, and in some sense, it says that probably this will be hard to improve. But anyway, this is something, and I think I was very pleased when Dennis came with the denominator 3 here, and that's all I wanted to say. Thank you.
Any questions?
Yes.
And what about the last theorem when Q is either solvable or a discrete subgroup
Solvable
or a discrete subgroup of a Lie group?
we don't know.
So can you make this work for like a metrical fibering instead of a
For
for metrical fiber instead of like
I see. Okay, Dennis didn't really try, but I think that his method can be pushed at least a little bit. Yeah. Yeah, maybe I should say that these are two cases where we know that the L2 compression is exactly 1, both for polynomials and for hyperbolic groups.
Any other questions? Okay, thank you again.
Thank you.